Welcome back, scholars, to a second look at rational functions. In today's video, we're going to continue looking at the key features of rational functions. Let's dive right in. Last time, we looked at discontinuities which resulted from values which were restricted from the domain. Those discontinuities appeared as vertical asymptotes and holes. We also saw that horizontal asymptotes could occur, but we didn't really unpack the details. In general, horizontal asymptotes behave a bit differently than vertical asymptotes. I like to think of these as horizon asymptotes because they tell us what happens on the horizon, meaning going far to the right or far to the left, or more specifically, as x gets very, very large or very, very small. Unlike vertical asymptotes, functions can and often do pass through horizontal asymptotes before they settle into their end behavior at the extreme values of x. So it's not formally correct to think of these as boundary lines, as they're often described in earlier math courses. Another difference is that a function can have at most one horizontal asymptote, while it can have many vertical asymptotes. Here's a couple of various examples of functions with horizontal asymptotes. Note that the example on the far right demonstrates that the function can pass through the horizontal asymptote, but ultimately at the extreme positive values of x, it veers or settles out near that line y equals b. So let's take a look at how to determine if a horizontal asymptote is present and what it will specifically be if it is present. Recall from our study of polynomials that the degree of a polynomial is the highest power or exponent of any term in that polynomial expression. Also note that the coefficient of that highest power term is referred to as the leading coefficient. So in this example f of x, if we had a polynomial ax to the n power, the leading coefficient would be a and the degree would be n. Similarly, in the denominator, the polynomial bx to the m power has a leading coefficient of b and a degree of m. Generally, there's three possible categories that a rational function may be sorted into. First, it could be that the degree of the numerator is less than the degree of the denominator. In this case, the horizontal asymptote is y equals 0 before any vertical translations, which would appear as a constant value added to or subtracted from the rational expression. The second possibility is that the degrees of the numerator and denominator are equal. This produces a horizontal asymptote at the value y equals a over b, where a and b are the leading coefficients of the numerator and denominators respectively. Remember that you may need to write your rational function in standard form or expanded form to see those coefficients. The third possibility is that the degree of the numerator is greater than that of the denominator. In this case, there is no horizontal asymptote. However, there may be an added bonus, which we'll look at later. Let's practice finding horizontal asymptotes for a few functions. On the far left, we have a category 1 situation where the degree of the numerator is 0 and the degree of the denominator is 1. So y equals 0 will be the horizontal asymptote, but check it out, there is a vertical translation down 4 units. So we'll need to translate that asymptote down 4 units as well. So we'll have y equals -4 here as our horizontal asymptote. Taking a look at the graph of that function, we can see that on both the left and the right-hand sides, the end behavior of the function tends towards that horizontal asymptote, which is shown in a dashed green line here at y equals -4. Next, in the middle, we have a category 3 situation where the degree of the numerator exceeds that of the denominator, so there is no horizontal asymptote. Finally, on the far right, we can see that the degrees of the numerator and denominator match. So our horizontal asymptote will be the ratio of the leading coefficients, which will be y equals 3 over 1, or just y equals 3. If we take a look at the graph of that third function, we can see this is an example of where the function crosses a horizontal asymptote locally. However, the end behavior again on both the left and the right-hand sides tends towards that value where y equals +3. Now, I mentioned that so-called category 3, where we might have a bonus. Well, it happens that if the degree of the numerator exceeds that of the denominator by exactly 1 degree, we can treat that fraction as division. If we follow through with that division, the result will be a line in the form of a linear equation. We refer to this as a slant asymptote. Before we look at those, I'd like for you to think about whether it's possible for a rational function to have both a horizontal asymptote and also a slant asymptote. Did you say no? You're right. Remember that if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. However, there may be a slant asymptote if the difference between the degrees is just 1. All right, let's bring back those long division skills. I know you can do it. To find the slant asymptote, we'll treat this fraction like division, where the numerator is the dividend and the denominator is the divisor. I added a 0x placeholder here in the dividend so that I can avoid mixing up my terms when I divide. We'll start by looking at the leading terms of both the divisor and the dividend. To get 4x to the third power, I need to multiply x squared by 4x. After subtracting out that part of our dividend, we get the next term in our quotient by multiplying x squared by 5 to get 5x squared. We'll end up with a remainder of x minus 2 over our divisor here. Our slant asymptote is going to be the quotient without the remainder. I encourage you to think for a few moments why we exclude the remainder here. Remember that a horizontal or a slant asymptote tend to describe the end behavior of a function, or as x gets very large or very small. Well, the value of the remainder becomes so small that it is effectively 0 as x reaches those extreme values. For that reason, it's not necessary to include the remainder in our equation for the slant asymptote. Here's a look at that rational function, which is pictured here in blue. The slant asymptote, which is located at y equals 4x plus 5, is shown as the dashed green line. We can see that as the x values get very, very large or very small, the function tends towards that slant asymptote. Let's put everything we've seen together by looking at one rational function. I recommend that you start by writing the function in factored form so that we can use the form most suitable to describe each key feature. I've shown this function not only in factored form, but also in lowest terms, with common factors reduced to 1. The domain is best visualized using the factored form. We'll have two restricted values located at x equals -2 and at x equals +3. This breaks our domain into 3 intervals. Next, I'll specify the types of discontinuities. I can see that x equals -2 will be a vertical asymptote, while x equals 3 will be a hole, since it's a removable discontinuity. I'll use the standard form to evaluate whether we have a horizontal asymptote. Since the degrees of the numerator and denominator match, we'll have a horizontal asymptote located at y equals the ratio of the leading coefficients, which is 2/1 or just y equals 2. That could produce a break in the range, but we'll check the graph to be sure. Finally, to find the zeros, I'll use the expression in lowest terms to find what value of x causes the numerator to be equal to 0. That will be at x equals -1/2. To find the y-intercept, I just set x equal to 0. I'll use the lowest terms expression here, and that will be y equals 1/2. Okay, that's quite a lot of information about rational functions for one video. These concepts are usually taught over several lessons, but hopefully this provides a good refresher, as many of the concepts were already relatively familiar to you. Next time, we'll look at how to solve rational equations algebraically. See you then.